Here's a quick review of digital audio in depth when finishing a project. Bit depth relates to dynamic range. That's the difference between the loudest and the quietest signal. When looking at an audio graph, this is the up and down axis, where we think of volume. So the taller it is, the higher the volume. Mathematically, the higher the bit depth, the better the capture of a low-level signal. So this is where the richness of your recording lies. This is the decay of an instrument. This is reverberation. This is the spatial cue of a nice-sounding recording space. Sample rate, on the other hand, relates to frequency. This is on the horizontal axis, the left and right axis. This relates to time. The higher the sample rate, in theory, the higher the frequency that you can record. Together, these two things plot out the contiguous audio waveform onto a graph. Or you can think about it building a wheel out of Legos. So of course, the more Legos you have, the smoother it's going to roll. When you're recording, you want to have the highest resolution source as possible. The National Academy of Recording Arts and Sciences, in their recording guidelines, recommends a minimum of 24-bit 48K in your recording process, preferably higher. Why do higher sample rates sound better when standard microphones can't even capture frequencies up that high? Most people can't hear up that high either. Why isn't 44.1 good enough? The answer lies in a problem called aliasing. When recording at a lower sample rate, you have to put a low-pass filter at the upper limits of the frequency range of your recording. And cheaper low-pass filters cause a distortion called aliasing. You don't have to know this for the test. It creates this shadow that you can actually hear in the lower frequencies if this is done incorrectly or it's not done at all. If you record at a higher sample rate, you don't have to worry about this. The distortion frequencies are pushed out of the human hearing range. Bit depth, on the other hand, relates to dynamic range. And when we're thinking about our Lego or our graph paper analogy, 16-bit resolution only has 65,000 steps about, and 24-bit has 16 million steps. You could see that there's a huge difference in the detail with which we would be able to record. Thinking about how to measure this in exact terms, each bit of word length that you add adds 6 dB of dynamic range. That means that 16-bit equals 96 dB of dynamic range, and 24-bit equals 144 dB of dynamic range. The more steps you have, the more likely it's going to be able to plot your contiguous waveform onto your piece of graph paper. If it can't, if it has to estimate something, this is called a quantization error. The place where this is most likely to occur is as close as you can get to the noise floor. This is where the decay of your notes, this is where reverberation, this is where the spatial cues of the room lie. So it's the detail and the richness of your recording. Trying to plot out even just a simple line, you could see that it's not going to be able to plot it out exactly. It has to plot it out in steps like this. This is an example of that distortion. Over here, when we're looking at a waveform, you could see that if we're not at a higher level, the likelihood is it's going to have to square out these representations that it makes. One problem that happens when we're doing recordings is we have this high resolution recording, but then we have to distribute it on a medium like a CD, which is 16-bit 44.1. And the larger squares are more likely to create this quantization error and aliasing when converting. So when we are converting, the first thing you need to do is convert the sample rate. So the next step, change the bit depth. This is done by adding Dither, which is low-level randomized noise. Dither helps to diminish this quantization error and capture low-level signal like decay, reverberation, and spatial cues. This is down below where we generally listen to things, but it helps diminish this quantization error and capture these low-level signals by making the signal wider. On the left side, you can see that there are a couple of steps here that can't necessarily be represented. If we add this noise, it makes the waveform wider, and it makes it so we can actually capture that noise. Because we are adding noise to our signal when we do it, we want this to be our absolute last step, because if we do that first before we do the sample rate, we're more likely to have problems with our audio. So, in summary, these are the things that you need to remember for the Pro Tools test. You always start with the highest resolution possible and maintain quality for as long as possible throughout your production process. If you're converting to CD, you do the sample rate conversion first. Then, if you need to go from a higher bit depth to a lower bit depth, that is where you add dither. Dither relates to dynamic range, it relates to bit depth. And of course, because you're adding noise, you only want to do dithering once.